Right?
Sir, 16 students.
No, 16 total are there, but right now only I am seeing 14 students. Now they are coming, I think. Okay. So you are recording this, right?
हो ते रेकॉर्ड होईल सर.
Yes, sir. Yes, sir.
Mhm. Shall we start?
येस सर तुम्ही स्टार्ट करा आता आलेत ना 15.
So good morning to all. So now
Good morning, sir.
morning. So I am seeing now there are total 17 people. So out of which I think 15 are students probably, 15 or 14. Anyway, first of all, let me first welcome you to this our mass spectrometry lecture series. That is your part of the syllabus only. So how many of you are familiar with the mass spectrometry? You can.
Sir, it is quite new.
You are quite new. Okay. How many of you are
Yes, sir.
basically BSc in chemistry? How many of you have chemistry background? Many?
No, sir, only 3 students.
Only 3 students. Okay. Anyway, but I will tell you, since you are a part of the bioanalytical, and mass spectrometry is the very interesting and most useful application, or I will say technique in bioanalytical. Without mass spectrometry, no work can be carried out in the bioanalytical field. So mass spectrometry is the most crucial, and one must understand, because as I understand, you are all going to be bioanalytical scientists of the future. Many of you will work after your second part is over. You will work in the government labs or maybe private labs, or you may some may pursue your PhDs also, or maybe I don't know subsequently other educations also. So in view of that, and since you have chosen bioanalytical as a career, knowing about a mass spectrometry, not only for getting marks, but for your career point of view, is the most important thing. Because mass spectrometry is a very, very practical subject. It is not a theoretical subject only for just somebody has to learn in the college and forget. It is not like that. Mass spectrometry is a very, very practical subject, and without mass spectrometry, as I said, there is no bioanalytical chemistry really. So one must understand really the mass spectrometry well. Now, before we go into the mass spectrometry, what we will be touching on is that we will touch on some of the few basic concepts, because I know since many of you are you don't have a chemistry background, but what we will try to do is that we will build up the subject very, very slowly. We will not do it very hurriedly. So now let us see the first of all, let us go to the anybody knows what is mass spectrometry? You might not have known the details of the mass spectrometry, but what is brief about the mass spectrometry? Anybody can tell me?
Sir, it is used to detect various compounds, and it is used to measure the through mass of the compound. It something like that.
Now, what is special about mass spectrometry? As you are already in the second part, you must have learned a lot of chromatography, right?
Yes, sir. Yes, sir.
So you must have learned GC, HPLC, right?
Yes,
So
sir.
gas chromatography. What is the prerequisite of gas chromatography? Can I analyze all the molecules by gas chromatography?
No, sir. Mainly volatile compounds, sir.
Volatile compounds. So volatility. So I always say, if I can evaporate, then I can separate. Okay. If I am able to evaporate the compound, then I will be able to separate the compound on gas chromatography. If I can't evaporate the compound, it is not a vaporizable compound, then I will not be able to do gas chromatography. Similarly, you have learned about HPLC also. So what is the prerequisite for doing a liquid chromatography or HPLC? Just like somebody you have said already. And I want everybody to answer, not only one person. Huh?
Sir, their affinity towards solvent,
No, is it affinity?
mobile phase.
Is it
Uh,
affinity? No, I am talking about prerequisite. Without that, you cannot do HPLC, or without it, you cannot do liquid chromatography. What is that? Just like you are
Sir,
told.
it is the affinity towards the column.
No,
That is how it will get retarded,
no.
maybe.
See, column affinity comes afterwards. Before I talk about column affinity and other things, I should be able to introduce the compound first, right?
Yes, sir. Yes, sir.
So, what is the prerequisite for introduction of the compound in the HPLC or any other liquid chromatography?
Sir, sample preparation.
Dissolution. I should be able to dissolve the compound in the liquid. So we call typically mobile phase or maybe some solvent, right? So unless I am able to dissolve the compound, I will not be able to do any HPLC or any liquid chromatography. Everybody agrees with this?
Yes, sir.
Yeah.
Yes, sir. Yes,
yes,
sir.
sir.
Now, so I can say when I am saying gas chromatography, if I can evaporate, I can separate. Similar chromatography, I can say if I can dissolve, then I can resolve, right? If I am able to dissolve, then I can resolve. See, these terms have been coined just to help us in memorizing or nothing else other than that. Okay. So now, if I have to say how many compounds, I am all talking about currently the organic compound, because see, bioanalytical means bio it terms there is organic, everything is mostly organic in nature, right? So if I have to do GC, I must evaporate the compound. If I have to do HPLC, I must be able to dissolve the compound. Now, what is the prerequisite for mass spectrometry? Can anybody tell me?
No idea, sir.
No idea. See the how many? If I say 100 compounds in the organic chemistry, just as I am just telling an example. How many I will be able to do GC? Maybe a few of them. Maybe 20-30% I should be able to do GC, because each and compound cannot be done. You cannot evaporate it. And if let us suppose I want to do HPLC, I will be able to do maybe another remaining 70%, because I will be able to dissolve majority of the compounds. So unless I am able to do any of them, I will not be able to do the GC or HPLC. Now, when it comes to the mass spectrometry, since the principle is the mass, measurement of a mass, okay, every compound in this world, it has got a mass, right? So since every compound has got a mass, I will say GC is a specific technique for compounds which can be evaporated. HPLC is a specific technique which are for the compounds which can be dissolved. Whereas mass spectrometry is a universal, because each and every compound in this world, it has got a mass. If it has got an existence, it has got a mass. Everybody agrees with this?
Yes, sir.
Yes,
Yes,
sir.
sir. Yes, sir.
Yes.
Sir, can you
So
repeat?
naturally, I will say in some broader terms, GC is a specific technique, HPLC also is a specific technique, but whereas mass spectrometry is a universal technique. Any compound in this world, you can analyze by mass spectrometry. See, there will be some practical limitations afterwards, because we are not going to do purely mass spectrometry. We always do mass spectrometry coupled with a chromatography, either it may be GC or it may be HPLC. So because of those things, some limitations may come. But if you talk about general, mass spectrometry is absolutely universal technique. And any component, if it has got an existence, it has got a mass. And naturally, I will be able to analyze by mass spectrometry. So with this brief background, so you can imagine, if I can analyze any kind of compounds, so molecular weight, there is no limitation. See, GC again I am coming to, which are the compounds I can evaporate? I will be able to evaporate those compounds which are generally low molecular weight. If it is a very high molecular weight compound, Can I evaporate them? I won't be able to do that. For example, plastics, which are so higher molecular weight. So there I will not be able to basically evaporate any plastic, and naturally I will not be able to GC. Similarly, some of the compounds which are not, I will be able to dissolve them. I will not be able to analyze by HPLC. But as I said, mass spectrometry, most of the compounds I will be able to analyze. So it has got a very broader applications, and any kind of molecular weights. If you talk about proteins and peptides, I won't be able to do any GC. But mass spectrometry, yes, I can do any amount of mass spectrometry. If let us suppose polymers, which has got a molecular weight of 2 million, 5 million, 10 million, I can do mass spectrometry always. I won't be able to do GC for those compounds. So mass spectrometry is a technique, but I won't be able to using the mass spectrometry for the compounds which are very simple to analyze. Although it has got a very broader applications and it can be used for many compounds, I will always use the techniques selectively. If something can be analyzed easily by GC or HPLC simple, I will first use those techniques, or maybe titration, I will use first those techniques. Subsequently, those compounds which I am not able to analyze by those techniques, I will use the mass spectrometry, or maybe some unknowns are there which I want to identify, I will use the mass spectrometry. Is this brief background clear to everybody?
Yes, sir.
Yes, sir. Yes.
Yes, sir.
So
Yes,
now
sir.
let us see little bit about the mass spectrometry. First of all, I have forgotten to introduce myself. My name is Dr. Narendra D. Gangal. I work for NOCEL, which is we are in the field of rubber chemicals. We manufacture chemicals for rubber, that is additives, antioxidants, accelerators. I am currently working as a Vice President, VP, Quality Assurance, TQM, Analytical Research. There are 2-3 departments. And this, my email ID, I am just giving. So can you see my this first slide?
Yes, sir. I can see.
Yes.
Yes.
Sir.
So
Yes, sir.
ndgangal@gmail.com and cell is 98205-23794. Okay. So you can note down if any queries afterwards in your next syllabus of our mass spectrometry, you can ask me or you can send me message. Now let us go to the mass spectrometry basics. Okay. Now mass spectrometry has been a very old technique. If I am little bit going to talk about historical perspective also, because why historical perspective? Unless you know how much people have worked on the mass spectrometry, you will not be able to appreciate the really the importance of the technique. So and one more just small thing I will tell you, we will have after 30 minutes we will take a 5 minutes break. Okay, and we will
Okay,
again.
sir. Okay.
Yeah. So the J.J. Thomson, who built the first MS prototype to measure the M by Z, that is mass to charge ratio. Now, whenever we deal with the mass spectrometry, we will not talk about a mass. We will talk about mass to charge ratio. Because the technique is such, it doesn't understand the mass on absolute scale. It understands only mass to charge ratio. Now, what is charge? What is exactly how it is M by Z is measured? That we are going to learn in a subsequent lectures. So this J.J. Thomson was awarded the Nobel Prize. Then Aston also worked a lot. This was in 1906. Aston worked a lot on this in Cambridge. He again did a lot of experimentation in 1919. He designed to measure the mass of elements. Aston again was awarded Nobel Prize. If you see the overall history of mass spectrometry, minimum 5 to 6 scientists, they got the Nobel Prize in mass spectrometry. And one of the most latest, I will say, the person, not a Nobel Prize, but who did the, I will say, the greatest work in the field of mass spectrometry, particularly organic mass spectrometry, is F.W. McLafferty. He was alive till recent days and recent years, and he expired. But he did really the fabulous work. Many of these which I am showing in the current just now is basically they worked a lot on the technique, whereas the McLafferty, FW McLafferty, Fred W. McLafferty basically worked on the applications part. So let us see the further history. So then in 19th century again there were many scientists like Goldstein, Wien, Thomson, as we already discussed. Somebody said that at that time the mass spectrometry principles were not so known. So somebody said this is a canal rays. Somebody said no, these are maybe similar to the hydrogen particles and so many things. So in 20th century, as I was talking, Thomson did a lot of work. He separated neon 20 and neon 22, and he correctly identified basically the by embodied 11 signal as the 22 neon particles. Thomson got a Nobel Prize, as we already discussed. So these are the scientists which worked. We'll just skip little bit and we'll go to the Dempster, 1936, Arthur J. Dempster. You can see the last line is there. He again did a lot of work on the mass spectrometry, and he developed basically some of the ionization sources. Now, what is ionization sources? I know you don't know right now, but we are going to discuss that afterwards in detail. So he worked a lot on the basic, some of the modules of the mass spectrometer. Then a little bit we'll skip on 1943. If you can see, Westinghouse marketed its first mass spectrometer, and so you can see the mass spectrometer on commercial scale was made as early as 1943. So you can see such a long history it has. Almost for last 80 years, people have been working on the mass spectrometers as commercial mass spectrometers. And at that time they called it a new electronic method for fast and accurate gas analysis. 1956, the Fred W. McLafferty proposed a hydrogen transfer reaction that was subsequently known as McLafferty's rearrangement. So McLafferty is considered to be a father of modern organic mass spectrometry. And 1959, Dow did work on the mass spectrometry. They coupled GC, gas chromatograph coupled to the mass spectrometer. First GCMS, which is hyphenated technique, was developed. Then 66, the chemical ionization was developed. Then somebody in 68 developed electrospray. See, today if you see, electrospray is a very popular technique, if in LCMS particularly, and it is developed as early as in 1968. You can imagine. See, in the recent time, in last 20 years particularly, a lot of development further has taken place because of the development of computers. I will say 30 years particularly. Computer, the softwares. Earlier, the machines used to be very big machine. I will show you the photograph of the first initial mass spectrometer. They were all very broad machines, big machines, and lot of analog aspects used to be there. Subsequently, after the computers got developed, and a lot of improvements came. Then I will go to the 1980s. Koichi Tanaka used ultrafine metal plus liquid matrix to ionize. So Tanaka was basically the person who invented the modern mass spectrometry ionization technique, that is MALDI. So Tanaka was given the Nobel Prize. So you can see 2002, Jonet Fain and Koichi Tanaka were awarded 1/4 of the Nobel Prize in the chemistry each for the development of soft desorption ionization methods for spectrometric analysis of biological macromolecules. See, majority of the macromolecules are very big compounds, and doing the I will say successful ionization of these techniques is not so easy. So Tanaka developed basically the technique for that. The early mass spectrometers, you can see such a big machine and then no electronics at all, absolutely zero electronics, very less I mean say. This is the current mass spectrometer. It is a Finnegan machine. There are many companies who work on the field of mass spectrometry. One of the most pioneers in the earlier was this Finnegan Corporation, that is Finnegan MAT, which was earlier called Finnegan MAT. Subsequently, it became the Finnegan Corporation. Now today it is called Thermo. So Thermo is they are the original people of Finnegan mass spectrometers, and there are many others, like there are Shimadzu's are there. Then there is Agilent is there, Perkin-Elmer is there. There are many who basically developed a lot of mass spectrometers, which are I will say benchtop models. What you are seeing basically is a LCMS, which is again a benchtop model. Looks quite complicated, but very simple to operate and gives a lot of information. Any questions? Any questions?
No, sir. No, sir.
Okay. So we'll proceed further. So now, what does a mass spectrometer do? Now, before we go to this slide, how many of you know how many techniques of mass measurement are there? How many techniques? Are you aware of the mass measurement techniques?
No, sir. I haven't heard of it.
No, you don't know how to do measure the mass.
Not exactly, sir.
There are many. You have learned chromatography or no? If you have learned chromatography, you must have came across with the either GPC, gel permeation chromatography, or size exclusion chromatography. Do you remember anybody? Anybody remembers?
Yes.
Yes. So size exclusion chromatography is typically which is basically for the measurement of masses, because in size exclusion chromatography the name itself suggests size exclusion. So or it is alternately called as gel permeation. So basically it has got a gel structure inside the column. You inject the sample gets introduced into the column. The gel has a typical structure whereby the smaller molecule they pierce the gel structure more, and the larger molecule they bypass the gel structure. So the largest molecules they come out from the column first and the smallest molecules last. So you get the peaks, which are basically the based on their molecular weights. So this is one technique which is very typically used and popularly used today for molecular weight measurement. But again, it is for the quantifications and other things. It is not for identification. Unless you have got a standard, you won't be able to identify those things. Now, and identification also, it has got limited capabilities. The second technique which is typically used is that you have got the viscosity average molecular weights. So viscosity measurement also another technique which can be used for the molecular weight. Now mass spectrometry, it doesn't do, as I said, it doesn't do the mass measurement. What it does is that it basically it does the mass to charge ratio it measures. So it measures, everybody is able to see the slide?
Yes, sir.
Okay. So it measures the mass better than any other technique. Okay. And it can give information about the chemical structures. So what are the mass measurements good for? It is to identify. So now when you are a bioanalytical scientist, you are going to work on the many different new processes or new products. Now you can see, for example, currently the corona is going on, and the corona is going on. There are two pathways going on in corona. Everybody is familiar with corona because you have no choice also. Everybody must be familiar. So either there is a vaccine somebody is trying to develop, and then second is that you are trying to develop the drug which can kill the virus. So when it comes to the drug development, why it is taking time? Anybody knows why drug development is taking time?
Sir, because of trials, human trials, something.
But why trials? Why not? Why you cannot introduce directly? You just see whether the virus is getting killed and introduce that.
Sir, because it is required for regulatory bodies.
Is it for regulatory?
It can be toxic for
But
humans.
actually, it is for human
Test.
safety.
Yes. It is for you and me. Regulatory is only a, I will say, window in between. So that nobody should do any uncontrolled work. That is why regulatory is there. Regulatory is basically for you and me. It is not for somebody else, right? So unless you know that that particular drug molecule or the drug, this thing has been chosen for this killing virus, is it friendly with the humans? If it is not friendly with the humans, then it has got very limited role. But because it may kill virus, but if it kills the human also, then what is the purpose of that drug? It has got no purpose then. So that is why knowing about the drug. Then secondly, drug when it is administered in the body, drug doesn't remain as a drug. Drug will undergo interactions with our body, right? Our various aspects will be there in the body, it will interact, and drug will form metabolites. Because what is the purpose of the drug? Purpose of the drug is to introduce that body, that particular compound inside the body through either oral or maybe injectable or anything, and the drug has to basically counter the negative aspects which are happening in the body, and after it does that, it rectifies the whatever the issues which are there in the body. At the same time, after that it has to get out from the body, right? Drug is not for storage in the body. It is for the killing some of the unknown things which are maybe viruses, bacteria or other things or other bad effects. So it has to do the work and it has to get out. So naturally, any drug when it is developed, first of all, the efficacy of the drug is important for the targeted components. That is what for it is targeted. That is first thing. Secondly, is that drug forming some metabolites which are harmful in nature? That is second. Third is the drug is getting stored inside the body or it is going out immediately. So all these things are very essential. So the mass spectrometry comes into picture to identify, verify, quantitate all kinds of metabolites, recombinant proteins, protein isolate natural sources, drug candidates, all sorts of things. So the mass spectrometry is basically used for all those things. So in drug metabolism or drug, I will say identification, the new drug synthesis or all the research, if there is no mass spectrometry, no this kind of research is possible. So mass spectrometry is absolutely backbone for any medical research. So what we'll do now, it's already 31 minutes are over, so we'll take a break for 5 minutes and maybe 10:35 we'll again start. Restart. Okay.
Okay, sir.
Okay, sir. Okay.
So we'll continue.
Yes, sir.
Yes, sir.
So you can see the slide.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So let us see the applications of mass spectrometry. I am just going to read out the titles only. Huge applications: bioavailability studies, drug metabolism, characterization of potential drug, degradation, screening, identifying drug targets, protein peptides, oligonucleotides, pesticides, soils, groundwater, so many things, forensic analysis. Everywhere the mass spectrometry is utilized. See, the MS principle, different elements can be uniquely identified by their masses, and we will be dealing mainly about the organic mass spectrometry, whereby there will be carbon, hydrogen, oxygen based compounds. How the mass is defined? Everybody remember this basic definitions? Assigning a numerical value to the intrinsic property of a mass is based on using carbon number 12, that is carbon 12 isotope as a reference point. So 1 unit of a mass is defined as a dalton, and 1 dalton is defined as 1/12 the mass of a single carbon 12 isotope. So 1 carbon 12 isotope is considered as 12.0000 dalton. So it's a very it is not something like decimals. There are 236 or something like that. It is 12.000. So that is a reference point. And any mass which when I am going to measure, it will be the 1/12 of the carbon isotope is considered as 1, that is 1 dalton. And related to that, you are familiar with the SI system, everybody?
Yes, sir. System International.
Right. So in SI system, typically it starts with the meter is there. You know where is the meter? How do you define meter? Anybody knows?
No, sir. No.
See, meter is as everybody knows, it is 100 centimeters, but over a period of time, there cannot be any change in this. So, because it should not happen, the meter used by India is something different, and meter used by Australia is different, and that is why there has to be complete global harmonization, right? So, in order to have the global harmonization, the SI system, they have made a meter. They have made a meter which is a physical meter has been kept in Paris and which is considered as the basic meter available in the world, and any measurements are basically related to that meter. So it is similarly here. Here we are considering 12 is going to be the carbon 12 isotope mass and 1/12 is going to be the 1 dalton. So that's the relative measurement. Now carbon has got isotopes also. Anybody knows which are the isotopes carbon has? How many isotopes carbon has? Anybody has any information? First of all, do you know what is isotope? Anybody know isotope?
Yes, sir. It is the different forms of same element.
No. That's not a definition. See, how do you define basically the any material? It has got a fixed number of protons, right? And fixed number of neutrons. Any
Right.
material has. Now, the number of protons, what do you call it that? It is basically the atomic number.
Atomic
Right?
number.
It's the atomic number. And whereas when I say proton plus neutron plus electrons, that becomes a atomic mass. It's atomic mass. So number of protons is basically that gives me the characteristics of that material. So whether the neutrons differ, still the compound is same. So in case of carbon, it has got an isotope of carbon 12 and it has got an isotope of carbon 13. So isotopes are those compounds which has got the same atomic number but different mass. Is it clear, everybody? So here
Yes,
carbon 12, it has got the same atomic number, that is number of protons are same in 13 also and 12 also, but atomic mass is different. One has got a mass 12, another has got a mass 13. So I call it, these are the two, but it has got a mass number is same. Basically the atomic number is same or the number of protons is same. Okay, because number of protons give the characteristics of the atom. So carbon will be the carbon, whether it has got a 12 or 13, but masses are going to be different. So this is the isotope. So carbon has got carbon 13 as another isotope and carbon 12 is the main isotope what we see, and it is quite in good abundance. If you see overall, around 1.1% of the carbon is carbon 13 in the world. So wherever you may see maybe 100 kilos of carbon or maybe 1 ton of carbon or 10 tons of carbon or anything, you will always have 1.1% of the atoms in that will be carbon 13 and remaining 98.9 are going to be carbon 12. Now let us see mass to charge ratio. What is mass to charge ratio? Now why mass to charge ratio? First of all, are you familiar with the UV spectroscopy? You have learned UV spectroscopy. You will learn just now. We saw the basic requirements of HPLC and GC. Similarly, UV spectroscopy. What is the requirement of UV spectroscopy? Anybody? Anybody knows UV spectroscopy? You have learned or no?
Yes, sir.
Yes.
You have learned. What is the requirement? The first requirement is going to be the compound which is under analysis should absorb in that UV region, right? If it doesn't absorb, can you analyze the compound by UV spectroscopy? You will not be. Okay. Now, so that's the requirement of a UV visible spectroscopy as such. Similarly, infrared, if I say, it must have the vibrational excitations. If unless it has got a vibrational excitations, it will not be able to show me the infrared. But that's the property of the technique itself. It is not a basic property of that compound or anything related to that every material should absorb UV. It is not like that. But if I have to analyze the compound by UV, then I must have that compound must have a UV absorbance that is required. Similarly, in the mass spectrometry, if I have to analyze the compound by mass spectrometry, then I should be able to do ionization of that, and I can measure only mass to charge ratio, because mass to charge ratio measurement is basically the technique which is the basic aspects of a mass spectrometry. So if let us suppose you say I don't want to determine mass to charge ratio, I want to determine only the mass. Then mass spectrometry is not a technique for you. You have to choose some other technique then, right? Because mass spectrometry needs ionization, and because it can only measure mass to charge ratio. It cannot measure absolute mass at all. Absolute mass measurements can be done by gel permeation chromatography, or it can be done by the other techniques. But mass spectrometry, mass measurement is always through mass to charge ratio. So where from this charge comes, that we are going to learn in ionization and other things. So this is the prerequisites. So if let us suppose, now since we do not have blackboard, I cannot show many things. I have to only discuss verbally. Let us suppose I have got a mass of 1000. Okay, I am telling you I have got a mass of 1000. I have ionized it. It has got a charge of 1. What will be m by z? 1000 divided by 1. How much is that? 1000?
1000.
Right.
Yes,
Now
sir.
let us suppose the same molecule I am able to ionize it and I am having a charge of 2. Okay. So I will have 1000 divided by 2. So that will give me 500. Everybody agree with this? Right? Now there is a
Yes.
third molecule which has got a molecular weight of 500. When it is ionized, I have got a charge of 1. So it is 500 divided by 1. Right? So it becomes again 500 mass to charge ratio. Now, if the first compound whereby it has got a charge of 2, the first, there are 3 examples we took. 1000 divided by 1. Now you leave that example aside. The second example which I said 1000 divided by a charge of 2, that becomes mass to charge ratio 500. The third example I said 500 is the molecular weight and it has got a charge of 1. So 500 divided by 1 is the third example. Now the mass to charge ratio for the second case and third case is different or same?
Same.
Same. It has got both, as although the molecular weights are different, it has, in the second case we saw the molecular weight of 1000 but charge is 2, that is why m by z became 500. In the third case I saw the molecular weight is 500 but charge is 1, so again m by z becomes 500. The mass spectrometer will not understand whether it has got 500 divided by 1 or it has got 1000 divided by 2. It will only tell you mass to charge ratio is 500. That's it. It is you have to see whether it has come from the dual charge, whether there a charge is 2 or charge is 1, or all those things have to be learned afterward. Means basically by interpretation part. Okay. So the mass spectrometer does not know the molecular weight. Now let us suppose if it would have been known the molecular weight, it would have told you that no, one is 1000, one is 500, but it doesn't know because it has got only a measurement of mass to charge ratio. So you must understand the limitation of mass spectrometry. Although it measures the mass very accurately, it doesn't measure the mass on absolute scale. It measures the mass only by mass to charge ratio, which is basically the technique. It is I will say the heart of the technique. So if somebody wants to do on absolute scale the mass measurement, then mass spectrometry is not the technique, right? Now let us see the a typical mass spectrum. And everybody is able to see this?
Yes, sir. Yes.
So on the y-axis, what is there? It is arbitrary units. Basically the, I will say, response. Okay. Or I will say the abundance, you can say, consider in this case, the percentage abundance. And on the x-axis, you have got a mass to charge ratio. So typical mass spectrum will look like this, whereby you have got small blips will be seen. Some of the peaks will be seen bigger one, some of the peaks will be smaller one. Unlike the gas chromatography or HP, whereby the peaks you will find they will be Gaussian in nature, right? Whereas here they will be sharp lines like a line spectra, because every peak corresponds to one typical m by z ratio. Okay, so it is basically identification of molecular mass, determination of structure, determination of elemental composition, determination of isotopic composition, quantification. It can do quantification a lot, in the sense the accuracy or the sensitivity of the mass spectrometer is much lower than many other techniques which are traditionally used. For example, a typical, if you see HPLC, you must be familiar with different types of detectors. Anybody can say any name few detectors in HPLC?
Sir,
FID.
UV detector.
And any other?
FID.
UV, and what is the next?
Sir, flame ionization detector.
Is it used by HPLC?
No, sir. Sorry, sir. It is using GC.
HPLC, which are the other detectors typically used?
PDA
RI,
detector.
everybody is familiar. RI, refractive index, fluorescence. All these are the typical detectors which are used by HPLC. Okay. Now, typically, if you see UV, you will be able to see parts per million. That is, how many milligrams per liter parts per million? 1 ppm means 1 mg per liter, that is 1 ppm, right? Now, if let us
Yes.
suppose
Yes.
I want to do further lower, UV will have limitation, that is HPLC UV will have limitation, but mass spectrometry can do the easily the analysis. Mass spectrometry, the sensitivity levels can go up to 10 to the power minus 15, that is femtograms, and ppb or ppq up to people can go if you design the technique properly. So mass spectrometry is, in addition to its identifying power, which has got a tremendous identifying power, it has got a very high sensitivity, and that is why you will find typically now in the sports you will find so many tests are carried out on the sports persons. Anybody can tell me what are the typical tests and which the person becomes very controversial also, or sometimes he is barred?
Sir, doping
Yes,
tests,
whether
sir,
they
Doping
take
used
test.
in
doping
Olympics.
test.
Absolutely right. So doping test, do you think which techniques are typically used for doping test? It is mass
Sir,
spectrometry.
urine mass spectrometry, sir.
Yes. So what you do, you take body fluids, and then you have to do either LCMS or GCMS depending upon the targeted compound. But only mass spectrometry can help you because it has got a power of identification. At the same time, it has got a power of detection also. That is sensitivity, both at a time. So that is why mass spectrometry is very common technique for doping and many other places. Forensic sciences everywhere, mass spectrometry is utilized. Now, this is a typical mass spectrum of a standard compound and decane. Okay, decane, everybody remembers? What is decane? I have shown you already structure. How many carbon
10
numbers?
10.
10 carbons.
10. So it is typically an alkane, right? What is alkane? Molecular weight, molecular formula? Alkane, I am saying.
CH4.
CN H2N plus 2. Right, that is alkane. Now you can see here the decane, how many C10 it has got. Okay, if it is C10, it is 12 into 12, it is 120, right? And plus it has got H2N plus 2. So 10 into 20 plus 2, again 22. So 120 plus 22, that comes 142. So 142 is the molecular weight of decane. Can you see the first peak of 142 here? A small peak. Can everybody see a small peak of 142 shown?
Yes.
Yes or no?
Yes, sir. Yes, sir.
Yeah. Unless you are
Yes,
Yes,
physically
sir.
yes, sir.
able to see that. Anyway, so now can anybody tell me which is the difference which has shown other than 142? What is the number which is shown typically? 14, 14, 14. Can anybody see?
Yes, sir. 14, 14.
There is a 14, 14, 14 typically shown. So the you can, when you want to read a mass spectrum, you have got a relative intensity on the y-axis and mass which are shown on the x-axis. So the first one, the largest one, typically corresponds to the molecular weight of that compound. Typically, I am saying this is a thumb rule. It is not always, because there may be other complex, association complex and other things. Typically, the highest you can see the M by Z is going to be corresponding to that particular molecular weight. Okay, and it is typically called as molecular ion. Okay, the next ones which I am seeing a small fragments. Okay, now here I will just show you. You are able to see this, na?
What, sir?
Can you see the slide or no?
Yes,
Yes, sir. You can
Yes, sir.
see the slide.
So I am showing the cursor. Can you see the cursor?
Yes.
Yes, sir.
So the cursor is where the highest intensity is there. Anybody knows what is this called? This is called base peak. So in a mass spectrum, the highest molecular weight which is seen, or M by Z, is typically, as I said, this is only thumb rule I am saying. There will be a lot of differences also. Is typically will corresponds to the molecular weight of that particular compound, and the highest molecular weight, highest intensity peak will be called as the base peak. All the remaining things are going to be called fragments. When base peak also is a fragment, but base peak is considered to be, it is a fragment which is considered as 100. It is considered as 100, and all the remaining fragments will be calculated based on the percentage relative abundance with reference to the base peak. So base peak, if I consider 100, this peak I am showing, let us suppose it has got a 90, and maybe subsequently this has got 35. So I will say this 100% I will call it, then this may be 90%, I will call this 35%. Like that, there will be a table will be made, and I will call basically that table as, it is the mass list. It is typically the mass list. Now you forget about this part. This is some different compound. I'm right now I'm just talking about the mass list. So the mass to charge ratio will be here in one column. The relative abundance will be here. Again, the mass to charge ratio is here. The relative abundance is here. So right from the lowest molecular weight or a lowest m by z to the highest m by z, it will be listed. Okay, and it is called mass list. Now you can see here. Can anybody tell me what is the base peak in this case? What is the mass base peak here?
100,
100.
17.7.
100, sir.
100
Uh,
relative abundance.
Base peak I am talking about. That means you are not understanding.
69.
Huh? Base peak I am saying
69.
69 is the base peak.
100.
Because why I said
Yeah.
highest m by z is the base peak, which is considered as 100, and all the remaining fragments, they will be relative to the base peak, right? So naturally in this list m by z is 69, relative abundance I have shown 100. So you have to choose, when I ask you about base peak, you have to choose m by z which is showing relative abundance 100. So in this case it is 69 which shows 100. So everybody agrees with this?
Yes, sir, exactly.
And you can see 131 is again a very prominent fragment. 209 is a very prominent fragment. 264 is a very prominent again fragment, 13.4. If you try to go and see which is the highest molecular weight peak, now you can see here 0.2 for 503 is 0.2 is very small. It may be noise also, we don't know. We have one has to check. So it is possible that the highest molecular weight or maybe m by z may represent a molecular ion or it may not represent molecular ion depending upon the compound. Now in this case you can see a typical compound which is 671 is the molecular weight here, but I can't see 671. That is because the molecular weight is high and molecular ion abundance is not much. See, we are going to discuss about the molecular ions abundance in detail in our subsequent lectures. But right now, I just want you to know about the terms. So when I talk about this is a mass spectrum, then what are the terms we have learned? The first term what we learned is the here, which is typically the, I will say the molecular ion possibility is there, that is 142. Then the highest molecular m by z peak I saw is the base peak. All remaining are the fragments. So are these terms clear to the people? Are these terms
Yes.
clear?
Yes, sir.
Any
Yes.
question, any question related to this? And my x-axis is always going to be m by z. You must remember, any mass spectrum you take in your hand, the m by z is going to be always on the x-axis, and relative abundance or relative intensity is going to be y-axis. See, similar to all other techniques, I am not interested in the percentage or I will say absolute intensity. I am interested always in the relative intensity, because depending upon the detector, depending upon the condition of the detector, my absolute intensities can vary, but my relative intensities will not change. They will always remain same. Now, as this particular mass spectrum which is recorded for one decane, N decane 142, it is very typical mass spectrum, and it has got a very high reproducibility. If let us suppose I have got a mass spectrometer in Birla College and I have got another mass spectrometer in say let us suppose Germany somewhere in some institute, it is going to show me the same mass spectrum on a typical given technique. Particularly if I say ionization source is same and my the mass separator also is same, then it is going to show me the same kind of mass spectrum. Now these all lab spectrums are typically called, they are the library spectrums and which have been taken using a quadrupole machine, and it has got a EI. EI is going to ionization source in this electron ionization. We are going to see the details of the ionization sources and other things. Are these things clear? Yes or no?
Yes, sir.
Okay. I think madam you are
Yes, sir.
students are keeping quiet. Anyway, let us go ahead further. Now, as I said, isotopes. Most elements have more than one stable isotope. Carbon I have discussed already. You have got 1.1% of the carbon, which is carbon 13. And mass spectrometer can see the isotope peaks if the resolution is high enough. If the resolution is low enough, then you cannot see the mass isotope peaks. If you can see typically hydrogen, it has got a hydrogen 1.0078 is there, which has got a 99.985 percentage abundance. That means any material of hydrogen if I take, always 99.985% atoms are going to be 1.0078 and 0.015 is going to be 2.0141, which is called deuterium, or there is another called tritium also. Similarly, carbon it has got 12, 98.89, 13 point is going to be 1.11%, nitrogen is going to be 14, will have 99.64. Like that, there is a whole list of tables in which you will find isotopes and their abundances. Now, if these basic little bit things are clear to you, then we will proceed with the mass spectrometry basic principles. Now, how does the mass spectrometer work? See, as I said, any technique, it has got a basic fundamentals. Now, unless in the mass spectrometer, unless you make ions, mass spectrometer cannot analyze. So, the first basic building block of a mass spectrometer is the ion source. Ion source is a must prerequisite for a mass spectrometry. The second part is the mass analyzer or mass separator, you can say. It's a mass analyzer which separates the ion. And third building block is going to be mass spectrum, which is present the information. This is going to be typically computer system. Now why ion source? Because that's the prerequisite of a technique. If I say in the infrared, why there has to be a source of lamp or the infrared source? Because that's a basic requirement of a technique. If that technique requires that, that machine will have those components. Similarly here, any technique in mass spectrometry, again mass spectrometry there are a lot of variations. You will have quadrupole techniques, you will have magnetic sector instruments, you will have time of flight techniques. These are typically the mass analyzer parts. If I talk about ionization sources, you will have electron impact mode or EI mode will be there, or electron ionization mode it is called. Then you will have chemical ionization mode will be there, you will have electrospray will be there, you will be thermospray will be there, you will have APCI. These are all variety. But when it comes to the mass spectrometry, you may have variations in the mass analyzers or you may have variations in the ion source. The variations can be there in this, but the three building blocks are always going to be there. Any machine, whether it is a mass spectrometer, it always will have ion source. It may have different ion sources, but it will always have ion source. It may have different types of mass analyzer, but it will always have a mass analyzer portion, and it will always have the computer based system. Okay. Now this computer based system will have different software. Somebody may use Unix, somebody may Windows, different kinds of depending upon the suppliers and other things. But these three building blocks are common. Is this clear?
Yes, sir.
So now
Yes, sir.
let us see the further in detail about the mass spectrometer block diagram. Okay. You have got an inlet, because inlet is basically, what is the inlet in GC? In GC inlet is there or no?
Yes, sir. Inlet port is there.
What is you typically called? That is injection port.
Yes, sir. Injection.
Called
Yes.
injection port. What are the variations in injection ports?
Sir, one is the manual one which we inject and then load. We do
I'm talking about
we
GC.
do manually.
I'm talking about GC.
Yes, sir. GC.
GC. See, you are talking about automated ports or these things. These are the automated or manual. I am talking about variety of injection ports. Whether you do manual injection or automated injection, there are varieties of injection ports or variety of injection systems. What is that? You have heard about the splitless?
Yes, sir. Yes, sir.
Yes.
Splitless.
So splitless is one type. Then you have got a purge pack is second type. Then you have got a cool-on column is going to be third type. Like that, there are many types of injection ports in GC. Similarly, in HPLC, you will have Riodan injector will be there, which is basically automated injectors will be there. Now, when I say talk about GC particularly, I have got different variety of injection ports because variety of compound needs to be analyzed. Similarly, in mass spectrometry also, my inlets are going to be varying. Either I may be able to use direct injections, that is one thing, whereby I do not chromatograph a system sample at all. That can be one inlet. I take directly the material sample in a syringe and inject in the mass spectrometer. That is one type of inlet. Second type of inlet can be I couple my mass spectrometer to the GC portion. So the column outlet becomes my inlet. Or the third I can do the LCMS I couple or the liquid chromatography I couple with the mass spectrometer, so it becomes LCMS. So the outlet of the column in the HPLC that gets coupled to the mass spectrometer and becomes the inlet. So the inlet, the purpose of the inlet is to introduce the sample in a most appropriate way, in the sense without disturbing its composition. So representative injection into the system, that is the job of an inlet. Okay. Then ion second comes in the ion source. Now ion source we are going to see in detail what are the different ion sources. As I said, the prerequisite of a mass spectrometry is that I must have ions, because if you are talking about neutrals, mass spectrometer cannot measure that, because the technique has no potential to measure the neutrals. It is only through subtraction principle you can guess about the neutrals. But if it has to measure the neutrals, that it doesn't have the capability, direct measurements. It can only measure the ions. It can either measure the positive ions or it can measure the negative ions. So the ion source is a prerequisite of a mass spectrometer. It must have the ion source. Then once the ions are formed, these ions needs to be separated out based on their mass to charge ratio. If let us suppose once ions are formed and they have got different mass to charge ratios, but they are combinedly put to the detector will be completely confused. It doesn't know that this mass to charge ratio belongs to what. It is 51 or 52 or 53 or whatever x, y, z. So detector will anyway give the signal. So what I will need is that I will need some analyzer or maybe a sieving device, just like at home when we go on doing this screening of the wheat or any other grains. You want to determine or you want to separate out something from that. You use the sieve. Similarly here, the mass analyzer will work, which will go on analyzing or it will go on allowing the mass to jar ratios. Based on that, it may be doing one by one. Maybe 51 will be first, then 52 will be second, like that. There are again variety of theoretical aspects in mass analyzer, which will come into the detail afterwards. So the basic concept of mass requirement of mass analyzer is to separate the mass to jar ratio one by one and throw them to the detector. So the detector can measure them one by one. And the fourth detector portion is very required. That is because it has to detect, it has to show me the signal for the whatever the mass to charge I have put to the detector. It must show me the signal. Without signal, I will not be able to understand whether it has got any ions or not. And the fifth system comes to the data system, whereby it is going to be the computer based system. You want to have break or we'll continue?
Break. Same.
Just a 5-minute break.
Okay. So we break for 5 minutes. So we'll continue now.
Yes, sir.
आले का सगळेजण?
Yes, sir.
Okay.
Yes, sir. Oh,
So as I was telling you, so these are the now there is a something is shown here which is high vacuum system. Why this is so, that again I will explain you afterwards. First, let us first understand the building blocks. So now first of all,
Sir.
you have, yes, William?
Are you sharing the PPT? We cannot see the screen.
What I will do is that I will send you the portion of the PPT, because this PPT is a full mass spectrometry. Okay, I can share the portion of the PPT which has been taught to you today.
Okay, but I am talking about screen sharing. I cannot see the screen.
Okay, you are, achha, you PPT share. I thought, okay, now I am just showing you. Achha. What about screen sharing? Sorry. Can you see now?
Yes, sir.
Okay.
yes, sir.
I thought you were talking about PPT sending afterwards. Anyway, so now first of all, everybody is now completely convinced that mass spectrometry is a very powerful technique, right? It has got a tremendous identifying power. That is, it can be used for quality identification. That is one thing. So it is typically used for all kinds of biomolecules, drugs, metabolites, pharmaceutical compounds, the pigments, agrochemicals, everywhere. Wherever there is a new compound, mass spectrometry it is utilized. Just a minute. Huh? Sorry, there was some disturbance. Yeah, so we are all convinced that mass spectrometry is a very powerful technique. It has got a identifying power. It has got a very high sensitivity. So it is used typically for the identification of all kinds of unknowns, including the doping. Then it can be used in forensic. It can be used in drugs research, pharmaceutical, metabolites, everywhere. Now, it has got a prerequisite just like GC or HPLC, that you should be able to ionize the compound. The compound should be ionizable. But as such, in a broader terms, it's a universal technique, because as I said, since every component has got a mass and you can do mass spectrometry that are. But one of the things will be required is that we should be able to ionize the compound. And for doing that ionization, we will have the ionization sources. So a mass spectrometry does not measure the mass, it measures only the mass to charge ratio, M by Z. Z is the charge, M is the mass. So, and for the basic components of the mass spectrometer are inlet, whereby I am introducing the sample, the ion source, which basically generates the ions, then mass analyzer, which separates the different mass to charge components, and then detector, which basically detects the mass to charge components and it gives the signal, and data systems, whereby it gathers all the data and it basically puts in a structured way and shows the mass spectrum, so that you and me can understand. Because if, let us suppose it is like a electronic data, you will not be, so it has to show in a presentable way, so it shows that. So that is a data system. Now, if you see schematics, now high vacuum pumps, our high vacuum system, the first one, it has got a turbo pump, diffusion pump, rough pumps, rotary pumps. See, I am just going to read at this moment, but we are going to discuss many of them in detail. Inlets, now there is no sample plate or anything. We have got HPLC, GC or solid probes. The ion source is there. There is a MALDI is there. Then there is the electrospray, ion spray, FAB, LCIMS, EICI. Mass filters will be TOF, quadrupole, ion trap, magnetic sector, FTMS. Detectors will be many like microchannel plates, electron multipliers, hybrid detector, data system like that. Now, depending upon the variation in the ion sources or mass filters, there will be different combinations of the mass spectrometer. Something may have MALDI and with a TOF, something may have ESI with a quadrupole, something with a ion spray with ion trap. Like that, there will be various combinations. Now, high vacuum system, that is turbomolecular pumps, is very common today. There are oil diffusion pumps also are there. Inlets, as I said, there will be HPLC, GC, or there will be injections. Ion source we are going to study, out of which will be studying the 4-1, that is EICI will study, MALDI will study, ESI will study, thermospray will study, FAB will study. Mass analyzer portion will study time of flight, quadrupole, ion trap, magnetic sector, all these will be studying. Detectors will be studying again microchannel plates, electron multipliers, photomultipliers. Data system, there are variations in that. Now, first of all, why the high vacuum system? Now, anybody of you has seen the mass spectrometer? How many of you have seen the mass
No,
spectrometer?
No.
Nobody has seen? But your first year training, I think there used to be mass spectrometer. No? You used to work in the labs, whereby generally the bioanalytical labs. After the first year training, no, this year it may not be there because there was because of Corona, right?
sir.
Yeah, we're going next year.
Next year,
We
next
have-
year on February.
Yes.
Okay,
Second
February. So those who have not seen, or maybe you have seen in the some books or something, a mass spectrometer needs a very high vacuum system. Why it needs a high vacuum system? Let us go into the details. See, most of the mass spectrometers, they work in the high vacuum condition, typically 10 to the power minus 4 to 10 to the power minus 5 torr. Now, the major reason in this that is that a mean free path. Now, when in the ionization source, when the molecule is bombarded with in the ionization source and ions are formed, see, you do not want these ions to interact with each other, right? You want them to be intact, and those intact ions should be measured. So that is why there is something called mean free path. That is the average distance that our ions and molecules will travel before colliding with another ion or molecule. Why we should avoid this? Because if let us suppose I have got a m by z of say let us suppose 85, and then there is another m by z of let us suppose 75. Two ions are there. If I am not keeping the good mean free path, there is a possibility that these two ions may collide with each other. If they collide with each other, they will interact with each other and they may exchange their energies. If they exchange their energies, it is possible the ions may get lost also. So then, whatever the ionization source is generating, I will not be able to see those ions. So that is why the mean free path is typically which is defined the average distance that our ions and molecules will travel. When they will travel? After the ionization source. So in the ionization source, the ions are formed, then they will travel to the mass analyzer portion. So this is the average distance that our ions and molecules will travel before colliding with another ion or molecule. This we must avoid. So if let us suppose I am keeping a sufficiently higher mean free path, let us suppose 1 meter. Generally, most of the mass spectrometers are less than 1 meter. If you see in the pictures also or in the books, you will find a mass spectrometer portion of the GCMS or LCMS is not more than 1 meter. It is less than 1 meter. So the analyzer portion is less than that. So naturally, if the mean free path is kept around 1 meter, then my ions which are formed, they will never collide with each other. Because once, as I said, I was telling you, there is 85 and 71. The 85 and 71, once they are formed in the ion source, they will go to the mass analyzer one by one, but directly. They will not basically meet each other and they will exchange the energy. Okay. If they exchange the energies and they will interact each other, then their identities will be lost. It is possible they may form adduct or they may neutralize each other, whatever, it may something. So the basically whatever the ions form in the ionization source, that I am not getting. So I don't want that. So that is why high mean free path needs to be maintained. So high mean free path can be maintained only if my all other gas molecules inside my mass spectrometer system is removed. So that is possible only by evacuating it. I go on evacuating the mass spectrometer portion in such a way that my vacuum becomes 1 into 10 to the power minus 4 or 1 into 10 to the power minus 5 torr. So very, very small. So there is no gas molecules at all. So naturally when there are no gas molecules, there is enough space available for my ions to travel. They will not have any obstruction. They will not have any interaction with other things. So naturally they will remain intact and they will travel uninterruptedly without any obstacles to the analyzer portion, and that is what we want. So that is why the mean free path should be 1 meter, and for keeping the mean free path 1 meter I must have a vacuum of 10 to the power minus 4 to 10 to the power minus 5. Now this 1 meter comes, let us see. We can see the average distance a molecule travels between collisions. Now length is equal to 4.95 divided by P. Now P is measured in terms of torrs. If let us suppose if I say 1 into 10 to the power minus 5, okay, if 1 into 10 to the power minus 5 torr, if I say it, you take it 10 to the power 5 here, then it is 4.95 into that, multiply by that. If you calculate properly, this is in terms of, it comes to the finally centimeter, this comes to 100 meter, 100 centimeter, which is equivalent to 1 meter. So this is a simple calculation for that. So if I keep, let us suppose 5 into 10 to the power minus 5, I keep, and then my vacuum is that much, I will have a typically mean free path of 1 meter, and when I keep a mean free path of 1 meter, I will not have collision of ions with each other or other gas molecules, and naturally I am able to maintain my ions intact, and intact ions, if they travel to the my mass analyzer, they will be measured properly. Is this fundamental clear to everybody? Why high vacuum? Why so much of silence is there?
Yes, sir, understood.
Understood? So you need a high vacuum.
Yes, sir.
If let us suppose there is no high vacuum, what will happen? If there is no high
So there
vacuum,
may be high chance of collision.
yes. But what will happen with the collision?
The ions may interact with each other.
Yes, and their identity will be lost, right? If
Yes.
they do not have the same identity what is formed in the ion source, then I will not be able to get reproducible mass spectrums. Today, if I say, let us suppose in Birla College, I have done the mass spectrometry and my vacuum is low, I will not get the same book type or library spectrum. I will get something different because my whatever the ions are formed, they are not remaining intact. So my mass spectrum will be bad. It will not be matching with my library spectrums. So I must get a reproducible spectrum today, tomorrow, after 5 years also. It must be the same mass spectrum for a typical molecule. So for doing that, higher mean free path or maybe the higher vacuum is required. So vacuum system is typically the two types of vacuum systems are there. There are typically two pumps. I don't know how many people have you used the pumps in the laboratory? Pumps have been used by
No, sir.
no pumps at all. For filtration, you don't use pumps. In I think BSc you must use
Yes, sir. Vacuum pump.
Yes,
Yes, sir.
sir. Yes, sir.
vacuum pumps. Vacuum pumps are typically the V-belt pumps. You will find one pulley is big, another pulley is small. Have you seen the pumps anytime? They are called V-belt pumps. Okay. So V-bed
Yes.
pumps are typically rotary pumps. They are called, basically the technical name is rotary pump. Okay. Now rotary pumps are basically very rough pumps. They are not for a very high vacuum. So what we'll need is that if you have to generate high vacuum, you will need combination of two pumps. Okay. Now this combination of two pumps, either it can be a diffusion pump coupled with a rotary pump, and it can be a turbomolecular pump coupled with a rotary pump. So these are the two systems that are typically used. So the old diffusion pumps were typically the old pumps, and today diffusion pumps are not used much. It is mainly turbomolecular pumps are used, because rotary pumps, you can read here, typically generates a vacuum of 10 to the minus 2 minus 2 to the minus 4. That's not enough for me. I need typically minus 5 torr. So 10 to the minus 5 torr can be, I can generate only through turbomolecular pump and diffusion pump in combination with the rotary pump. Turbomolecular pump, you can see here, a turbomolecular pump typically, it has got a series of blades or airfoils that spin at 30,000 to 90,000 rotations per minute. This tends to deflect. Now you can see this portion, the upper portion, is a portion of a mass spectrometer. Okay, from where the suction is being done. The pump is sucking. Okay, and whatever the gas molecules are seen here, they are thrown out by these blades. So these blades are moving continuously. So these some molecules are thrown down, then this again down, like that it is thrown down. So then the vacuum is generated, and then from here there is a connection to the rough pump. So what it does, it goes on pulling the gas molecules from the mass spectrometer portion downwards, and finally in a concentrated form it is thrown to the rough pump, and rough pump, which is typically rotary pump, which has V-bed pumps, they will be removing those gas molecules, and that is how the vacuum is generated. So this is the typically today used, which is turbomolecular pumps. It's a very efficient pump. It has got no oil, so naturally this will not show you any other spurious peaks or anything. Whereas the old diffusion pumps used to show sometimes the some spurious peaks because of the oil and other things. So TMP, which is typically the short form of the pumps, is very efficient device, but very delicate also in some way, because any misalignment in these pins will be, pump will go bad in no time. So any blockage or any other thing, but generally if they are well maintained, the TMPs will go for years and years, nothing will happen. Is this clear? TMP?
Yes.
So now the next pump is typically the oil diffusion pumps. Now oil diffusion pump, you can see again this inlet portion which you are seeing, where this is the upper portion is the mass spectrometer, which is connected with the pump. Now you will find there are vents, there is a heater block is there, and bottom of this heater block there is a oil. There is a typically very high boiling oil is there, means which is boiling point of the oil is very high. At low temperatures or ambient, it has got no vapor pressure, so very high boiling oil will be there. There is a heater block, and then there are vents, water cooling foils will be there, coils will be there. So this, what it does is that this heater block will heat, and it will heat up the oil. So oil, since it's a very high boiling oil, it will evaporate, not a very big way, it is smaller way. Those oil molecules will go up, and when they go up, when they get condensed back, it will take the gas molecules which are there here inside the oil, and those gas molecules along with the oil, they come down. They come down. This is a continuous process. It's a continuous process, and at this portion, the bottom, since there is a heating, the desorption of the gas molecules will take place from the oil, and which is connected to the rough pump or the rotary pump, and these gas molecules are continuously removed. Now the oil level is below than this, so there is no suction of oil through this. Oil only remains in the bottom. So the suction is only for the dissolved gas molecules from the oil in this portion. and it will be sucked to the rough pump, which is a rotary pump. So the oil diffusion pumps, which were typically used maybe few years back, maybe 10-20 years back. Today oil diffusion pumps are not used much. This is basically based on the diffusion principle. One of the disadvantages of oil diffusion pump is there is a possibility that although my oil is in the bottom and not connected to the rough pump, these oil molecules is the possibility something which is not condensed here in this portion may slightly contaminate my mass spectrometer portion which is on the top. So there is a possibility that oil may show some peaks in my mass spectrum. There is a possibility. So that is one of the major disadvantages of the oil diffusion pumps. One of the advantages of the oil diffusion pump is that there is no rotating device. See, you will always have here there is a big rotating device which runs at 30 to 90,000 RPM, and so when it is high rotations, there will be some maintenance related to that. Whereas in case of oil diffusion pump, there is no rotating device. It is purely the heater and oil which works, and the cooling of the oil and through this water cooling coils and vents and stack. So it comes down and finally it will give the high vacuum. So oil diffusion pumps, but still today oil diffusion pumps are not now they are not used much. That is because there will be always some spurious peaks because of the oil. And TMP technology has got standardized quite well and they work very efficiently. So is this pumps clear? That is high vacuum system clear? Can anybody tell me why you need high vacuum?
Sir, I have a question. I did not understand this.
Tell me.
Sir, can you explain again how the oil just once the gas is diffused,
I will tell you once again, and then you can ask me question then.
okay?
The oil is there at the bottom. Is that clear?
Yes.
Oil we have put
Yes.
into it already. Okay. There is a heater here. This because of the heater. One of the things that is oil is a very high boiling oil. Okay. So although I am heating at a very high temperature, it will not evaporate to a very large extent. It will only evaporate to a very small extent. Right? See the for example, if let us suppose if I got a hexane, okay, if I got a hexane, that hexane evaporation will be very fast because it has got a low boiling point. Okay, and once I heat up hexane, the evaporation is fast. The condensation, if I have to do, I will need a good cooling system, right? Whereas if I have got a high boiling material is there, like here, this is typically polyphenol ether is there. Now polyphenol ether, the boiling point is very high. Now as soon as the heating device hits it, there will be a small evaporation of oil, not very large. Is this clear?
Yes, sir.
Yes, sir.
As this evaporation happens, these oil molecules will go to the top. Is this clear?
Yes, sir.
Once
Yes.
oil molecules go to the top, since this oil is a it has got, there are water cooling coils and vents are there here, stacks. So there is a construction inside. Typically, there the cooling of the oil may take place, or the oil vapor will take place. This oil, whatever the gas molecules are there, which is coming from the mass spectrometer portion, this gas molecules will have solubility in the oil. Okay, and since it has got a solubility in oil, when the oil comes down by condensation process, it will bring down the gas molecules also along with it. Is it clear now?
Yes, sir.
Yes. So the first part is very high boiling oil, which has got a very high boiling point, and heating block is there. The oil gets evaporated very minutely, very partial. But since it's a very high boiling oil, as soon as it goes to the top and these gas molecules will have solubility in the oil, any cooling system it sees, it will immediately try to condense. It will try to condense, through the condensation it will come down. But when it comes down, it will always have the gas molecules from your mass spectrometer portion dissolve in that, and it comes down here. Again it sees the heater is there, it gets heated in this portion, then there will be desorption, because the dissolution of the gas molecules or the whatever the substance will be higher at a low temperature, whereas a high temperature the dissolution will be less. So as the condensed portion, condensed oil molecules, they come down and get heated up again, there will be some gas molecules be released again, which are trapped from here. And then this, as soon as there is a release of the gas molecules, there is a rough pump connected to this, and which will be driven. It's not a process which is happening on after 1 hour. It is a continuous process after every 1 minute, or maybe after every half a minute, or every 10 seconds. It is happening continuously. So that is why diffusion pump getting the vacuum is a long process. It doesn't happen immediately in 5 minutes. It goes on taking out small portions of the gas molecules. Clear now?
Yes, sir. Understood.
Any questions related to this? Still not clear?
No, sir. No.
Not yet clear? Or clear?
So no questions.
Okay. So now can anybody tell me why we need 2 pumps?
To create high vacuum.
But why 2 pumps? Why 2 pumps? High vacuum is the purpose. But why 2 pumps? See, as I said, these all oil diffusion pumps or turbomolecular pumps, they are basically the, I will say, the finishing pumps, or they will generate a high vacuum. But you will always need in couple with the rotary pump, which has got a suction capacity, and it will go on taking out the majority portion of the gases. The finer aspects will be done by these pumps. But these 2 pumps are not adequate on their own for generating very high vacuum unless they are coupled with a rough pump, which is like a rotary pump. So that is why they will be always in combination. Only rotary pump will have only the capability to generate vacuum from 10 to the power -2 to -4, only that much, or even less than that, -3. But if I use the rough pump along with the oil diffusion pump or along with the turbomolecular pump, I can generate a good amount of vacuum, that is 10 to the -5, because these pumps will be basically the finer aspects. They will small gas molecules which are remaining there, they will be taken care by the turbomolecular pumps or maybe oil diffusion pumps, whereas majority other things are already done by the rough pump. But that's not enough. That is why I need to couple. So they will be in series always. So there will be first portion of a turbomolecular pump which is connected to the mass spectrometer, and here I am connecting the rotary pump. So that is why we need a 2 pump system in a mass spectrometer, whereby it generates a high vacuum. Now why high vacuum? Because as the ionization sources, they will generate ions. I must keep those ions in an intact form. I should not disturb them, because then otherwise my mass spectrum will not be reproducible in nature. If let us suppose today I do not get these peaks, I showed you that decane. I showed you this decane. Now as I told you, if this is a compound which is taken today and analyzed in Birla College and analyzed in any other place in the world, it has to show the same mass spectrum. Because what is the purpose of this mass spectrum? Is 2 ways. One is to understand the molecular weight, and through the fragmentation pattern, it is a fingerprint. Just like our hand has got a fingerprint, or you have got thumb which has got a fingerprint. So this will be fingerprint of that particular component. And if I have to generate the fingerprint, I must generate that in a reproducible way. There will be libraries, like if I say NDK means it has to show me the same spectrum all the time. Then only the identification is possible, otherwise identification is not possible. So that is why high vacuum systems are very essential parts of a mass spectrometer, because without high vacuum you will not be able to get the ions in their original form, and you will not get a reproducibility of a mass spectrum. Is this fundamentals clear? Why I have vacuum system and what is the purpose of mean free path and everything? Any questions on this?
No questions, sir.
No questions. Okay. Now let us go to the inlets. What is the purpose of the inlet? I told you is to introduce the sample in the form of thin plug into the instrument with a GC, HPLC or mass spectrometer. So it has to introduce the sample in a reproducible way and in the same form. If let us suppose my inlet system, let us take a simple example of GC. I am keeping an inlet whereby there is a injector. On that injector, everything decomposes. Then I will be able to do the properly analysis. I won't be able to do, because if let us suppose it decomposes, then my component will not be analyzed in its original form. So inlet system has to keep the sample intact. Okay, intact in the sense its original form, and introduce that into the mass spectrometer. Basically the ionization source. That is the purpose of inlet. So we are not going to discuss much about the inlet system at this moment, because we will be separately seeing mainly GC and HPLC. GC is one type of inlet system and HPLC is another type of inlet system. The flow plates or the sample plates are very old thing now, and they are not part of the syllabus also. So there is a, you can just list down, like there is, if it is GCMS, there is a septum inlet will be there, or I can call GC inlet will be there. There is a direct probe inlet will be there. Now why direct probe inlet? Where some of the components, if I am not able to do either GC also or HPLC also, then they are very small form, material is very small quantity available with me. I may do it directly through the direct probe inlet. That is, I directly introduce the sample into the mass spectrometer without doing any GC or HPLC. Then GC inlet, which is typically common, so I call that GCMS, or HPLC inlet. I can have HPLCMS or LCMS. Direct liquid introduction, it can be, or direct gas introduction also can be there. So like that, the variety of inlet. And purpose of the inlet is, see, I am not going to discuss about the GC or HPLC, how does it work, because I presume that you know well GC and HPLC both, right? You have learned already in the first year. Everybody is familiar with GC, HPLC?
Yes.
Yes. So I am not going. So this is only the introduction about the inlets. So septum inlet, direct probe inlet, GC inlet, HPLC, direct in liquid. So purpose of the inlet is to introduce the sample into the mass spectrometer. Now what we'll do? We'll go to the ion source. In the ion sources, why first ion source? Is that the basic fundamental of a mass spectrometer is to do ionize the compound. It is like if I have got a paperweight and I throw that paperweight from my let us suppose to a distance of 5 meters. I throw it and paperweight breaks into different pieces, and again try to assemble my back those 5. Let us suppose there are 10 pieces are formed of the paperweight. I can see the 10 pieces and I try to correlate what is these pieces. I don't know that they are formed from the paperweight. So I am trying to correlate that yes, these 10 pieces have been formed. Are they really, can I say that they are they are originated from the paperweight? So if yes, then that is a part of the interpretation. Yes, then that is what I am trying to do. Now, why ionization or why the ionization sources are required? That's because that is the fundamental of a mass spectrometry. Mass spectrometry, if let us suppose I do not want to do ionization, then I am not doing the mass spectrometry, because mass spectrometry basically relies on the principle that materials are ionized, they are fragmented, and then they are thrown into the thrown to the mass analyzer portion. Then mass analyzer analyzes them, you get a mass spectrum, and from the mass spectrum you try to analyze the component back. So it is like looking back into the fragments or looking back into that. So and then try to interpret. So if let us suppose I want to analyze neutrals in their intact form, then mass spectrometry is not the technique. So mass spectrometry needs ions have to be formed. So it is like a paperweight thrown. If let us suppose I know that it is paperweight only and I don't want to ionize or I don't want to make the pieces, then I don't need the mass spectrometry at all. I don't know that it is a paperweight in the beginning. That is why I am ionizing it, or that is why I am making the pieces and trying to subsequently see those pieces whether can I correlate with something, some object, which subsequently based on my interpretation skill, I come to know yes it is a paperweight. Now the basic one of the fundamental is that my distance or the force which I give to the paperweight all the time is same, so that the fragments also are formed all the time are same. So based on that, depending upon how much energy I give and depending upon how much distance I am giving to the paperweight, my pieces will be there more or less. Let us suppose I have got a chalk and then I hammer that chalk with a 10 kilo hammer. The chalk will be completely converted to the fine powder, and at the same time I have got, let us suppose, a wooden block is there and I try to hammer that wooden block with again that same hammer. There will be difference in the pieces. Everybody will agree with this?
Yes.
Yes,
Because
sir.
wooden pieces, it is possible when it is a wooden block, it may form one or two pieces with that hammer, whereas the chalk may form completely the powder. It is possible. So if that is so, the molecules are also similar to that. Some molecules are like chalk, some molecules are like the wooden block. Means they are highly resistant to the fragmentation, or they are not very easy to fragment, and some molecules are they are very easy to fragment. So depending upon the type of molecule, now let us suppose if I take a wooden block and I convert into the pieces of three pieces are there, and I look back, I can definitely try to correlate, yes, it must have been coming from the wooden block of this size or something. Whereas if let us suppose a chalk powder is given to me, whether I will be able to make out something, the shape of the chalk? Anybody? Can I make out from the shape of the chalk from the big powder which is given to me?
No.
No, I won't be, because the powder is there. Yes. Somebody is saying the chalk powder, it has formed such a small pieces that I won't be able to see where from it has formed. I can just make out it may be a form from the chalk, but how was the shape of the chalk? What was the size of that chalk? I won't be able to make out anything. Whereas a wooden block, since it has got only three pieces, I may be able to join them and see, yes, it might have formed from wooden block of this much size to this much size. So there is a possibility of that. So that is why, depending upon the molecules which of my interest, I will have variety of ionization sources. Some ionization sources are going to be like which will give a very large fragmentation. Some of the ionization sources may not give large fragments. So what we will do now, we will stop here, and any questions if they are there, I will like to answer all of them, and next time we will take the ionization sources in detail. Are you now, first of all, why different kinds of ionization sources? Are you clear? Because I said that there are some molecules which are softer molecules which may get completely fragmented. Some of the molecules which are harder or they are more stubborn, they may not get fragmented. Naturally, depending on the type of molecule which I want to analyze, I will have variety of ionization sources. We are going to learn the ionization sources in our next lecture. Any questions for today's what we discussed?
No, sir.
Sir.
No? Everybody is clear?
Yes, sir.
Okay. So shall we continue or we'll stop? No answers? So we stop here now, because I know I do not want to give a dose of a very large concentration. So next time we will go to the ionization sources, but before that you must revise whatever we have learned. So we have learned about the today, first of all, why mass spectrometry, okay? Then what are the potentials of mass spectrometry? What are the applications of mass spectrometry? Then we saw that block diagram of mass spectrometry. Then we saw why high vacuum. Then we saw basically why mean free path should be higher. What is the purpose of that? And we saw the vacuum systems. These are the things we saw. And then we saw another thing was how to see the mass spectrum. What are the basic parameters of the terms used in mass spectrum? That we saw basically the molecular ion is one term which is used. The base peak is second term which is used. And third is the fragments. These are the terms. And so there is one is mass spectrum, second is the mass list. These are the terms we saw. So we stop here and we will meet again next Saturday. Okay?
Yes.
Okay, sir.
Okay. Thank you.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.
Thank you, sir.